Hello. In this presentation, Glenn Cho and I, Kwesi Rutledge, will be presenting our work on compositional safety rules for inter-triggering hybrid automata. This work was done under the supervision of Professor Nejmia Ouzeh at the University of Michigan's Electrical Engineering and Computer Science Department. The motivation of this work comes from the large number of cyber-physical systems that are being placed into our world today. For example, autonomous vehicles like the ones being developed by Cruise are currently being deployed by companies like Walmart to deliver groceries. One of the things that makes it difficult to deeply integrate these types of systems into our world is that it is hard to guarantee the safety of the vehicle when placed into an environment like this. On a highway, there are many different vehicles that can interact with a Cruise vehicle, including other autonomous vehicles and even human drivers. In Michigan's connected corridor, depicted on the right, autonomous vehicles are separated into their own lane to avoid reasoning about human-controlled vehicles on the road. But we argue that there are many cyber-physical systems where we cannot arbitrarily separate our systems from the rest of the world. Without the ability to cleanly separate our systems, there's a need for a method that guarantees the safety for collections of vehicles or systems, even when there are a very large number of them in the collection, and even when some human control systems are somewhere in the group. Methods for guaranteeing safety for large collections of systems with centralized controllers have been proposed in the past. They typically seek to find special recurrent operators or restrict their attention to affine or linear systems in order to simplify their task. For controlled systems, they can guarantee safety for systems with tens of thousands of dimensions. And for uncontrolled systems, these methods can verify safety for systems of up to 1 billion dimensions. There are also methods which seek to make guarantees with decentralized controllers. These methods use some combination of assumed guarantee contracts, control barrier methods, and symbolic abstractions to find controllers for individual agents that guarantee safety of the entire collection under some assumptions about the other agents. The limitations of each of these previous approaches are what we would like to address with this work. Centralized control approaches often do not have a principled way of finding the appropriate recurrence operators, or are restricted to work on certain types of systems, namely affine or linear systems. We note that many cyber-physical systems are nonlinear in some way, and thus these results may not be applied to them. Meanwhile, decentralized control approaches are sometimes difficult because it is non-trivial to find suitable contracts when systems are interdependent, and these controllers often require predefined constraints about how the other agents will behave in order to ensure safety. Predetermined constraints about other agents may be hard to identify, especially in environments where humans are involved. Another option for us to consider is responsibility-sensitive safety. Here we replace the assumption of knowing constraints on the behaviors of every system in the collection with the notion of not allowing actions that cause another agent to become unsafe. Thus, if all agents reciprocate this notion, then the system is safe. But if a rogue agent acts in a way that causes a crash, it is not the fault of a responsible agent acting reasonably. This is well suited to situations where humans are somewhere involved in the collection, as we do not need to exactly bound their behaviors. To incorporate responsibility-sensitive safety into large collections of nonlinear systems, we first introduce the inter-triggering hybrid automaton, a modeling framework to represent the collections we're interested in. Next, we define a two-part condition which is sufficient to guarantee the safety of an ITHA. And finally, we apply our framework with this condition onto several multi-agent control problems. Let us begin by discussing the modeling framework. The model for each system in the collection will be built based on the notion of a discrete time dynamical system. We will define such a system with the following tuple, composed of a state space, X, an input space, U, a disturbance set, D, and a dynamics function, which maps some combination of state input and disturbance to a next state. Given this definition, we can define the following set, which will be instrumental in our proofs about safety. The set is the robust controlled invariant set, and it is a set of states from which For any initial state in the set, there exists an input that can be executed such that the next state will be in the set regardless of the choice of disturbance from set D. With this in mind, we can define the intertriggering hybrid automaton. It is a collection of hybrid systems, each represented by a box in the figure, along with the resolution function rho, represented by circles in the figure. Each system is composed of three parts. The first part is the individual dynamics, which are dynamics as defined on the previous slide. The second part is the set of triggering actions shown in blue on each hybrid system. The third part is a reset function, which describes how the state of the system is reset given the current time, state, input, and combination of triggering agents. The set of triggering agents is determined by the resolution function in orange. The triggering actions of individual agents is combined in the resolution function bubbles and produces the signal which determines our resets. In general, this means resetting behavior for agent I is dependent on not just the triggering action of agent I, but the triggering actions of all other agents in the collection. To show the different components of an ITHA in a realistic setting, we now focus on an illustrative example. Consider the scenario of a collection of vehicles driving on a highway. The hybrid system model for the ego agent, in blue, can use the standard car following model as its dynamics. In such a model, the only variables of interest are the distance between the ego vehicle, in blue, and the car in front of it, in red, as well as the velocity of each vehicle in this pair. The inputs to the ego vehicle's individual dynamics are its acceleration, and the disturbance to the dynamics is the acceleration of the lead vehicle. The set of triggering actions in this setting are the possible lane change decisions. Each triggering action straightforwardly indicates decisions about lane changes. Finally, the reset map and resolution functions can be discussed. Recall that the individual dynamics are defined by the headway between the blue car and the car in front of it. So, if by some change of lanes the car in front of the blue car is now different, it should be the case that its dynamics are reset to reflect this. This is captured by a reset function, which changes the headway value according to rho I, which is the vehicle that ends up in front of the ego car after all lane changes are complete. The ITHA model can be used to address many problems in the multi-agent systems literature, but we highlight the following two problems which will be studied later on. The first is multi-agent control or supervision. This is the problem of finding local control policies or supervisors such that any execution where each agent uses such a local controller or supervisor is collectively safe. The second problem is single agent control or supervision. In this problem, the goal is to find a local control policy or supervisor such that there exist local policies for the other agents that ensure collective safety. In order to solve these problems, we must first introduce a set of compositional safety rules to guide the control inputs and triggering actions of a safe agent in the ITHA. In the next section, we introduce the two-part condition which is sufficient to guarantee the safety of an ITHA. Not all executions of an ITHA are safe, and in this work we introduce a method for restricting the possible control inputs and triggering actions of individual agents to guarantee safety. This requires us to develop self-safety, a condition governing the safe choices of control inputs, and rho hat responsibility, a condition governing the safe choices of triggering actions. Then, we show how the composition of these two conditions is sufficient for the safety of the collection. Self-safety of an individual agent indicates that from each state in the reachable set of that agent, there is a control policy which can guarantee its own safety when there is no resetting behavior. In the highway example, this means that a vehicle such as E has a control input which can guarantee safety assuming that no vehicle switches lanes. In other words, there is a control input that will keep it safe with respect to just the lead vehicle. In abstract terms, this indicates that agent I is self-safe if it is within a control invariant set within the safe set. So under the dynamics of F, which are in effect because there is no triggering, the state of the system will never escape the safe set. In this way, self-safety is a condition over the set of control inputs U at each time. We would now like to make a rule about the safety of triggering actions, like tau. The difficulty in reasoning about the safety of triggering actions is that the resolution function depends on not just one agent's triggering action, but all agents' triggering actions. So an agent must somehow predict what all others will do if it is to understand potential resolutions. Such a prediction will only be useful if it somehow over-approximates the true value of the resolution. We capture this by defining a category of estimates called a resolution over-approximation. The remainder of the examples we use in this presentation will be resolution over-approximations. An agent J is ρ hat responsible if its triggering action does not lead to safety violations of any other agent as expected from ρ hat. What this means in our highway example is an ego car executing the left action is ρ hat responsible if the action is safe given its predictions of what the other cars will do from ρ hat. For a prediction like what is shown in the bottom left corner, our ρ hat predicts that the vehicle in the middle lane will move out of our way, and so moving to the left in this case appears safe. Note that our estimation or prediction is only guaranteed to be safe only if ρ hat is an over-approximation. Often, our over-approximations contain a much larger set of possibilities, such as what is shown on the bottom right. In those cases, our action may not appear to be safe because of how conservative the over-approximation is. In an abstract setting, when we consider ρ hat responsibility of a control action tau I on agent J, we do the following. For every value of tau I, we evaluate the possible set of reset states according to ρ hat. These states are shown in cyan. If the cyan circle is entirely in the safe set, then it is responsible for I to take that action. If it is not entirely in the safe set, then it is not responsible to take that action. Note that this means that some actions, such as tau I equals 4 in the figure, will lead to a safe reset according to the true resolution, as shown in the black circle, but will not be entirely contained in the safe set, as shown in the cyan circle, and thus they will not be responsible even though they will lead to a safe resolution. Now, putting the rules together, we consider an ITHA a robust control invariant set for each agent's dynamics in the ITHA and a collection of resolution over approximations. The first result that we prove is that when given such information, there exists local controllers for each agent that are self-safe and responsible. The second result that we prove is that given the same information, if each agent uses a self-safe and responsible controller, then the executions of the ITHA will be safe. Furthermore, this result can be extended to talk about subsets of agents with self-safe and ρ hat responsible control laws. With the same initial information, if we are shown that some subset of the ITHA's agents, call that subset I prime, are using self-safe and ρ hat responsible control laws, then there exist self-safe and responsible control laws for all other agents. That is, all agents outside of I prime as well. The previous results are useful for controller synthesis for multiple agents or for a single agent, but you must identify appropriate control invariant sets and over-approximations in order to properly use them. Identifying such sets and functions is not trivial. We note that synthesis of robust control invariant sets for nonlinear systems is a field unto itself and direct the interested reader to that literature to better understand it. The part which is not well studied in the literature is finding ρ hat over approximations. So in this work, we discuss two methods for constructing them. The first over approximation is the trivial over approximation. In the highway example, this is equivalent to considering the possibility of every other agent taking any possible triggering action available to it. Surely one such combination of actions is bound to lead to the true resolution value. In math, this looks like creating a set of all the resolutions rho prime for which we can find there exists a suitable combination of some tau i's to create rho prime. The second over approximation arises from ordering in the way that actions are decided. You can consider this as possible in large multi-agent systems where some agents can signal their plans to others ahead of time. What this looks like in the highway example is an agent E can be aware of the actions that agent L1 and L3 are taking because they are in front of it. This can be due to the fact that the other vehicles have visible indicator lights to E because they are in front of E. This is analogous to an ordering over the set of all agents which can possibly vary over time. For such a general ordering, we develop an algorithm to find a less conservative over approximation. The result that we show for systems with such an ordering is that for ITHAs that share information in this way, our algorithm provides a guaranteed method for producing over approximations for each agent.
Finally, we will evaluate our framework on several benchmark control problems. A multi-agent control problem. B, a single agent control problem in the presence of uncontrolled agents. And C, a safety supervision problem. We will first talk about the multi-agent control problem, which we motivate with the following scenario. Consider a setting of n parallel processors, which are fed a series of external jobs. We can model this with an intertriggering hybrid automaton. The first component, the individual dynamics, are modeled as follows. The state space is defined as a set of natural numbers and represents the number of jobs in the queue for each agent. The control models the agent's choice to either complete a job or to sit idle, and the disturbance set represents the number of external jobs that are passed in. The dynamics can then be written as shown here, where external jobs are rejected if the state exceeds a throttle condition and throttle. The triggering actions for agent I come from the power set of agents that are connected to agent I in the connectivity graph G. The agent can also take the null action of not recruiting anyone. We can also write the reset map as follows, where the first case ensures that the queue length is always non-negative, and the second case updates the state considering agent I's control action, the number of agents that agent I has recruited, the number of agents that are recruiting agent I, and the number of external jobs. In this problem, we also define a stack overflow state, which occurs when the queue length for any processor reaches some n overflow greater than n throttle. The stack overflow state is a terminal state, and we would like to avoid these failures in execution. The figure on the left visualizes the individual system dynamics, while the figure on the right visualizes the connectivity graph, which describes the interplay between the different individual systems. Now, we turn to the control problem of interest. We wish to find a decentralized control policy for each agent, that is, without a central coordinator, which maximizes the throughput of the overall system while ensuring that no processor ever reaches a stack overflow. In order to do this, agents need to judiciously trigger the other agents. Careful triggering can help even out the queues over all of the agents so that individual agents are less likely to reach the throttle state. However, reckless triggering can cause agents to hit the stack overflow state. To solve this control problem, we formulate it as a receding horizon control problem, and for each agent, we solve an optimization problem. For agent I, we greedily minimize its own queue length, subject to several constraints. In particular, we impose the continuous dynamics, self-safety, that is, ensuring that the agent remains within its own invariant set, restrictions on which agents agent I can trigger, and responsibility, that is, ensuring that any triggered agents can remain safe for any control input. Note that due to the structure of the dynamics and the binary decisions that need to be made, the constraints are linear and the decision variables are Boolean. Thus, the problem can be solved as a mixed integer linear program. Different resolution function approximations can lead to different levels of performance. We compare three, which highlight the advantage of using a minimally conservative over-approximation. The first is a trivial over-approximation, where we assume that any agent that can trigger agent I will do so. The second is an under-approximation, which assumes that when recruiting agent J, no other agent will recruit agent J. As this is an under-approximation, it is in fact not safe. The third is the ordered over-approximation, which uses an index-based priority order. As this uses more fine-grained information on which agents can possibly trigger, it is less conservative than the trivial over-approximation. These insights are reflected in the results. The under-approximation B suffers from safety violations, while A and C are safe by construction. Furthermore, C can process more jobs than A because C is less conservative, and it can thus recruit other agents more efficiently. In our second example, we return to the highway driving scenario. As a recap, we control one agent, the ego vehicle, in the presence of other vehicles on the highway. Specifically, our goal is to control the ego vehicle to be safe and responsible with respect to the remaining uncontrolled vehicles while tracking a nominal velocity v nom equals 15 meters per second. We can again formulate this as an MPC problem. For the objective, we look ahead for a given time horizon and minimize the sum of squared deviations from the nominal velocity. As before, we enforce that the ego vehicle is self-safe. Then, if there is no reset, we also enforce the continuous dynamics. If there is a reset, and the ego vehicle chooses to make a left or right lane change, we update the ego state accordingly, and we also ensure responsibility by ensuring that any vehicle that is triggered by this lane change can remain safe under any control input. Again, we can model the Boolean decisions and conditional constraints with binary variables, and we can then solve this as a mixed integer quadratic program. It's quadratic this time because the objective function in this case is quadratic. We compare two resolution function over-approximations, A, the trivial over-approximation, and B, the ordered over-approximation that is described previously. Under over-approximation A, the ego vehicle travels 351.9 meters, while it travels 415.3 meters under over-approximation B, averaged over 25 random initializations of the uncontrolled vehicles. This makes sense, as B is a less conservative over-approximation than A. We can also compare the rollouts of the ego vehicle under the different approximations. Here, the red dot represents the position of the ego vehicle, while the blue dots are the positions of the uncontrolled vehicles. We can see here that under over-approximation A, the ego vehicle is extremely conservative and has to wait a very long time to switch lanes because of hypothetical lane changes from the other vehicles, while under over-approximation B, it is less conservative, leading to large performance gains relative to A. Finally, we consider a safety supervision problem in the highway driving setting. Specifically, our goal is to show that the ITHub-based safety rules can serve as a high-quality safety supervisor that provides rigorous safety guarantees while remaining sufficiently permissive. To do this, we show that our supervisor achieves low override rates when supervising on a real-world highway driving dataset, the HI-D dataset. The HI-D dataset is a large-scale highway driving dataset that was recorded on several sections of the Autobahn in Germany over several time periods. To quantify conservativeness, we count the number of times that our supervisor would override, the fraction of data points in which self-safety and row hat responsibility are violated. We want this override rate to be small because there are no crashes in the dataset, and thus any overrides can be roughly thought of as false alarms. And here is a visualization of the highway setting considered in the HI-D dataset. Finally, we compute the override rates on the trajectories in the HI-D dataset. Again, we compare two over-approximations, the trivial and ordered over-approximations. For self-safety, which is not dependent on the over-approximation used, we get around 10% overrides. For responsibility, the prioritized ordering has a much lower override percentage than the trivial over-approximation, 2 versus 28%. Overall, we see that the override rates are reasonably small, which suggests that our safety rules are sufficiently permissive. We now conclude by summarizing our contributions. We introduce a novel modeling paradigm for multi-agent systems, the intertriggering hybrid automaton. We derive an approach for proving safety of these systems using the notions of self-safety and row hat responsibility, which we show theoretically and empirically result in guaranteed safety for all agents. We describe methods for generating practical approximations of the resolution function and show how local communication can be leveraged to improve these approximations. Finally, we demonstrate our approach on single and multi-agent control problems and evaluate the conservativeness of our approach on a safety supervisor task using real highway driving data. Thank you for your attention.